Going to be going over optimization of an electromechanical device using multidimensional analysis software. If we can go to the next slide, Dennis. So the title of the talk this morning is Optimization of an Electromechanical Device with Multidimensional Analysis Software. I'm joined this morning by Kent Davey, a fellow IEEE member. He did his PhD work at MIT, and he's currently the editor of IEEE Transactions in Magnetics, as well as a consultant in the electromechanics and field modeling field. I'm also joined this morning by Dennis Peterson. Good morning, Dennis.
Good morning.
Dennis has a bachelor's in electrical engineering from the University of Manitoba, and he is a testing and benchmarking specialist with integrated engineering software for the last 15 years, and he will be walking us through their use of the software for this particular case study. If we could go to the next slide, please. A quick overview of Tecplot. I don't want to spend too much time on this, but we were incorporated in 1981, founded by Mike Peary and Don Roberts, both of which were working at Boeing. At the time, they were developing CFD codes, and for the first 15 years of our history, the primary focus of our company was developing computational fluid dynamics codes. One thing that came out of that was the development of Tecplot software, and that software is used for analyzing fluid dynamics results and other test and other simulation data. Today, we have over 50,000 users worldwide and over 100 academic site licenses. And domestically, if you look at the top 25 engineering schools, we have site licenses at about 85% of them. Our main mission is to help scientists and engineers explore data, discover information, and communicate results. Next slide, please. We have a suite of tools. The primary tools that we'll be talking about here today are Tecplot Chorus, which is a tool for evaluating overall system performance. We also have a Tecplot 360, which is probably our most common tool, which is for physics visualization, physics simulation visualization. And we also cater to the oil and gas industry for people doing reservoir simulation as well. Next slide, please. Today we'll talk more about simulation analytics and any of the other solutions we provide. Simulation analytics is the union of visualization, data management, statistics, and data mining for a set of CFD solutions, although as we'll show you here today, it's really agnostic. It's not necessarily limited to CFD data. In fact, it can be used for data of any type. And with that, I'll turn it over to Dennis.
Thank you, Darrell. I know some of our customers are attending today, but for those of you who aren't involved with electromagnetics, I'll just give you a brief view of Integrated. Our company started in 1984. Our first product was Electro, which is an electric field solver based on the boundary element method. And since then, we've developed a wide range of electromagnetic and coupled field analysis programs. We're unique in that most of our programs offer a choice of different solver methods, so our users can choose the best method for any particular application. And as a side benefit, this also allows you to cross-check results produced by the different methods. Now, for an overview of the agenda of the webinar, first we're going to talk about the basics of electromagnetic simulations of solenoids, and then I'll explain how you would use parametric analysis in our software to create model variations. I'll discuss rotational symmetric models because we'll be using that to generate a huge number of models for a case study. And then Dr. Kent Davey will be explaining how he would do a case study of a solenoid actuator and present the results in Tecplot. So when people talk about solenoids, usually they're referring to linear electromagnetic actuators, as I'm showing here, and you can boil them down to three basic components. There's some sort of a moving armature, a core, or a plunger, and we color that gray in the picture. There's an electrical coil, a multi-layer coil, multi-layer turn coil, which provides the magnetization. And then a ferromagnetic yoke or case, which we colored blue, and that provides the complete magnetic path. Now there are two types of solenoids. There's a pull type and a push type, and it's just a slight difference in the way they're configured but basically the same electromagnetic action. And I'm going to show you how those operate. I have some movies here. So first I'll show you a pull type solenoid. So here I have a cutaway view showing the components, and I've also overlaid a vector potential plot on some of the surfaces, and that gives you an indication of the magnetic flux paths. So once the coil is energized, that produces a magnetic force on the core, or the plunger, and that acts to pull it down towards the minimum air gap position. You notice we don't show any of the mechanical linkages or springs. So the core would be connected to something that is actually operating and some sort of a return spring. We're just showing the basic parts of the electromagnetic model. So that's our pull type solenoid. Now the push type solenoid, which will be the focus of Kent's presentation, it's the same basic idea. The magnetic forces move the armature, but the way the yoke is configured, there's sort of a hole through which the armature is able to push on something. So those are the two basic types of solenoids. Now, usually in any kind of a design, you're going to have to create a large number of model variations. Perhaps you have to investigate the performance of a particular prototype over its operating range, or you might want to try several different prototypes and again investigate how they're going to operate. So all of our software packages have a parametric utility which make it very easy to create these model variations. I'm going to demonstrate the parametrics with the first type of analysis, the range of motion type parametric, and I'll do that using the pull type solenoid, and I'll move the armature from its maximum gap to its minimum gap. So this is the way it looks in our 3D Amperes software, and I've shown the graphical interface for defining the parametrics. So now I'll open the Amperes program. This is our 3D magnetics program. Now here again on the exposed surfaces of the cutaway model, I've plotted the flux density, and I've limited the range of the flux density so that any density less than 0.02 Tesla will not be plotted. Now to show you, I've already defined the parametrics, how that looks like. So here we have a single loop and a single parameter, a gap parameter, and that's been assigned to the armature, and that will move the armature over 11 steps. So it will create 11 different model variations and solve each one of them. For each model variation, we'll calculate the force on the armature, and we'll also do a contour plot of the flux density. Now, just to show you what will happen, we can do a validation of the parametric. Now, this is actually moving the plunger through a dry run. It's not actually solving for the field values, but it shows you what type of motion you would get in the parametric. Now, I've already solved that in another model. Once you've completed the parametric run, you'll have the results summarized in a table, and these results can be copied to the clipboard, or you can graph them. So in this case, we'll use the gap displacement as the independent variable and the magnitude of the force as the dependent variable. And I've already done that again. Here's the results you get moving the armature from the maximum gap to the minimum gap. Down at the bottom, we have a force of 12 pounds. That's for the maximum gap situation. And once you've moved the armature all the way to the minimum gap, the force shows a huge increase. It's up to 200 pounds. So here again, I'm just summarizing those results with a picture of the starting and ending configurations. And again, you see there's a huge increase at this minimum gap. The force at the minimum gap is also called the hold force, and this will be central to what Kent will be talking about in his case study. Now, let's suppose that the hold force for this particular configuration, this prototype, was not sufficient. Two ways you might think of to increase the hold force. One would be to increase the number of turns of the coil or to drive the current higher. or you might increase the size of the solenoid. And so we can do that also using parametrics. Now, as we start talking about creating multiple prototype variations, now the number of models becomes huge. And 3D analysis software takes much longer than 2D software. So we're going to introduce the concept of rotational symmetric models. Here again, I'm showing a cutaway version of the 3D solenoid, and I've shaded some of the exposed surfaces. And then next to it, I'm showing what an equivalent rotational symmetric model would look like. Rotational symmetric models basically solve the field equations in cylindrical coordinates. And in cylindrical coordinates, there are only 2 degrees of freedom. So that's essentially a two-dimensional problem. And the advantage there is the speed advantage. It can be 40 to 60 times faster. Now, at this point, I'd like to launch a poll. And I'd like to find out from the people attending unfortunately, let's see. Okay, unfortunately our poll didn't work. Okay, I was going to ask about the number of people who are using three-dimensional software. Moving on then. Okay, here I'm showing in the two-dimensional rotational symmetric case how we would have a nested loop parametric where you would have both the current and the solenoid varying and also scaling the size of the solenoid. Now I'll show that in our two-dimensional software Magneto. So here I'm showing we have 2 loops. In the inner loop we're varying the current, and in the outer loop we're scaling the geometry. Now I'll do a quick validation of the parametrics to show you how that'll look. Now what's happening is that we're going in the inner loop through several different current variations, and in the outer loop we're enlarging the solenoid. Now at each model variation we're going to calculate the force on the armature, and we're also going to calculate the differential permeability. Now that will take some explaining. Whenever you're increasing the current of a solenoid or any electrical device, there's a possibility of saturating the steel, and a very effective way of examining that saturation is to create a differential permeability plot. So that's what we're showing here. Now this might seem a little bit similar to the flux density plot that you saw before, except the colors seem reversed. That's because wherever the flux density will be high, that's where you'll have saturation. So in this plot, wherever you see a dark blue color, that means that the steel has been saturated and its effective permeability is low. Areas which are red, the flux density is fairly reasonable and you're showing the maximum permeability. And some areas which are green, that's where you're at the initial permeability, where you have very low flux densities. So I've already solved that, and I can show you how those results would look. So here's our initial configuration, our initial size, and initial current. Now we'll start increasing the current. You'll notice that the blue regions are expanding, and you notice there was a transition there. I'll just go back. When we have an increase in size, we return to the initial current, and so that blue region shrink again. And so every 10 steps, basically, we're increasing the current, and then we have a size increase, and we return to the initial current. And as you can see, we're increasing the size of the solenoid. You'll notice that there are some parts of the solenoid where they're always red or orange. That means that those parts never really saturate. And as a designer, you would know that if you were trying to get more performance of the solenoid, there'd be no advantage to adding more steel in those regions. On the other hand, the regions that are very dark blue where they're saturated, you might think that making those parts thicker or larger diameters might give you some increased performance. Now, since we have 2 nested parameters, we will have not just a single curve results, but a family of curves. And again, I'll show that in another Magneto model. So here we have the solved parametrics. And when we graph these results, we have a choice of which one of our parameters will be the x-axis. I'm going to choose the volume current. And then the second independent variable will be used to plot the family of curves. We could plot each curve individually, or we can plot them all at once. And so we'll choose the size or scale parameter. And again, I've already done that. So you can see that here we have a family of curves. And for each curve, that's starting off at the initial current level, and then we increase the current scale, and then we go on to the next size of solenoid. Now, that was just a two-dimensional plot. You can also export these values into a CSV file and then import them into a Tecplot and create a project. Then you can view the results as a scatter plot, and that's actually quite a bit more interesting. And it'll become much more useful when Kent explains a multi-parameter optimization. Now at this point, I'd like to turn things over to Kent, and he'll be discussing the optimization and actual case study. So Kent,
okay,
if you could take it away. Oh, let me just go back a few slides. Sorry. Okay.
All right. In any real-world application, we'll almost certainly encounter multiple objectives and constraints. And one of those is often unwritten, and that is that the insulation maintain its integrity through the life of the product. And towards that end, you'll almost never want to analyze a device with a current constraint on the winding. But rather, if you have that ability, you should always use a current density constraint on the winding cross-section. And with that in place, you automatically satisfy the thermal constraint. So what are the independent variables? Well, those are the number of ways in which you can reshape the device. And the dependent variables are going to be, they always involve the objective and all the constraints. So let's go back to that push actuator that you heard Dennis describe just a second ago. Let's consider both a weight constraint and a fringe field limitation. The latter has to do with its proximity to additional electronic equipment. The former has to do with its aerospace usage. So consider this cross-section on the right. We're going to, again, use it in a rotational symmetric embodiment. And so the easiest way to do that is to look at three ways to reshape this device. Consider the first variable, we'll just call it variable x, and we're going to reshape the device by moving the right-hand side of that yoke inward. And that does two things. Not only does it reduce the weight of the yoke, it decreases the total amount of current that's going to be useful for creating force, hold-down force on that actuator, specifically the armature that's in the center. So we have a quick video shows you how that happens. You can see as it moves in that actually changes the shape of the upper two arms, lower and upper arm of the yoke, and of course changes the cross section. So the loop 2 will do something almost identical, but we'll compress it vertically. We'll take the lower section of the yoke and move it upward, and that again reduces the number of amp turns, total amp turns that you have for creating a hold down force, and it also reduces the weight of the yoke. So here, take a look at this video that's showing the same equivalent action, but this time vertically. It looks excessively compressed, but you have to remember that these are going to be nested loops. These variables, all the ones that you're seeing, are going to change in an integrated fashion. So let's go to the last parameter. We'll call it Z. And this time we're going to move all of the highlighted green segments in at the same time. And what that does is it preserves the amp turn product, and it preserves the shape of the yoke, but it changes the armature, that center structure, and squeezes it in. That changes the force radically and reduces the weight, but not so much as the other two variables had. So consider the video file showing this third parameter. Okay, so we've got three variables, and once you place them in a nested loop and you begin to run out the information that can produce, it quickly becomes almost overwhelming. In fact, with only a sparse number of points, I mean, 10 cubed is going to be 1,000 number of points. We just did a little bit under that. This is yielding 864 field space that you've got to investigate. Now here we've got X, Y, and Z, those three parameters that we chose to be our independent variables, and we're plotting the force as a color, and we're using the shape, the size of these little scatter balls to represent the weight. So we've got two of our output variables sort of represented in this three-dimensional figure, and that's one of the capabilities that Tecplot allows us to display visually. Get a little bit of a feel for how this armature is going to behave, but right away you capture the idea that those areas that are delivering the largest force are also the ones that are going to be the largest weight, and that's probably something that you would have assumed intuitively right away. So if I were just approaching this problem without any plotting capability like Tecplot, I would do the following. I would go ahead and take those independent variables and begin to represent the problem, all of the outputs that were significant, and I would represent them with a variable metric spline. And the reason I want to do that is because if I do that well, I can take the gradient and the second derivatives of all of those important second variables. And if you know anything about optimization, you know that both those first derivatives and those second derivatives really help in terms of making the optimization routines not only run quickly but run smoothly. And so I would then put all that information into a mathematical package such as a trust region algorithm and allow it to define the minimum of the negative force while subject to all the constraints. In this case, the constraint on the fringe field and constraint on the weight. And the way these usually work is they look at certain regions of the problem mathematically, and they fit. They call those truss regions, where you can fit a quadratic into certain parts of the problem, and then follow that portion of the problem down into its minimum into that region. But now that we have a tool, more sophisticated visual tools, even when I'm done with this, I'm left with the vague feeling I might have missed something. Have I fallen into a local well? Do I have a good feel for how the problem is beginning to roll out even when I get a mathematical solution? And so having the ability to look at this visually is just paramount importance at times. So here's a picture of all of the data against two of the independent variables, and you're looking at the field leakage on that z-axis, but the scatter plot balls are colored by that all-important force variable. So that's one way to look at these, at the entire 864-point set of data. Here's another set. Now you're beginning to get a little better feel for how the distribution of these scatter plots. Now you're looking at force, and you get in a little bit better picture of leakage. And remember that leakage was one of those constraints. And here it's not quite as obvious that some of the leakage is not associated with the high force value field. In other words, there are several solutions that deliver a wonderful force that really are not penalized with high leakage. And of course, those are very desirable. Here's one more plot, but this time the very desirable high force solutions have a very undesirable weight associated with them. So at this point, it's clear that we've got a lot of data, and sifting through 864 images and 864 solutions is a difficult process unless you've got a sophisticated plotting package, and this is where some of the capability of Tecplot can shine. So let's move into that. Here we're going to go into Tecplot Chorus. Now you're looking at two of our variables, y and z, and force is on that z-axis. But we've got the capability to begin to interrogate that data versus those three key parameters. I can filter it, for example. For example, I can go to the force, and I can begin to say, look, I only want values of force that exceed a certain level. So I'll begin to pick up this filter on a force value. As I do that, you see that some of the data images began to disappear. I can go to the leakage table filter and begin to drop out the leakage and say, look, I just can't have some of these higher fields because the proximity of electronic equipment didn't allow it. So I drop down the leakage field, and sure enough, it helps me to see that automatically there are several solutions that are just become disassociated. Same thing with weight. I know that weight, because of the aerospace application, was a premium, and so as I began to put in the weight filter, many of these solutions began to go by the boards. Now I can jump into this a number of ways. Here's the number of solutions that are available to us if we go ahead and put in forces that are greater than 6 pounds, weights less than 2.5 pounds, and leakage that satisfies 131 Gauss. No leakage greater than 131 Gauss. Now let's go back to Tecplot, and I'm going to put in by hand the criteria that I know that the sponsor was interested in. He wanted a force that was greater than 6 pounds, so I'm just going to enter that by hand. He wanted the leakage field that was greater than 0.013, 130 Gauss. So I'll put that in. Then he wanted a weight that was no more than 1.2 pounds. So when I put in these points, these criteria, I'm left with 3 cases. I'm going to highlight those 3 cases. Highlight those 3 cases. I'm going to ask Tecplot to show me what they look like. So here they are. I'm going to click on them and ask them to give me a little bit more information about them. What do they specifically look like? And how do they compare to one another? So if you look at this sidebar, you see, oh, this little table is telling me exactly what those independent variables were, X, Y, and Z. It's giving us a lot more information. It's telling us what the force is, what the volume of the armature is, what the volume of the steel, we call that the yoke, what that all-important leakage field parameter was, what the volume of the copper inside through which we were sending that constant current density, and what that all-important weight parameter was. Not only that, when I clicked on a little parameter just a second ago, I asked it to tell me how the other images were different, how they differed from the one that I've got highlighted. And now if I could draw your attention to this particular image right here, if we blow it up just a little bit for you, I'll bring it down. What you see is that the center structure gave us a little bit more steel on this lower section than this reference that we have highlighted, and that it seems to also have a little bit more copper in the center area. It's harder to see that, but the same thing can be said for this one. Well, how does it differ from this one that we have highlighted? And it's going to show the differences highlighted in black that draws our attention to the main differentiation between these. This is just one of these features that you can sort of use to your advantage in terms of saying, well, please show me the difference between these two. I'm going to go back to our PowerPoint, for example. This is the three cases sort of represented in a different fashion. The Tecplot highlighted for us. And we've got them graphed in a way that I want to highlight another differentiation. Here's where your engineering design judgment is going to come into play. Notice that I've got weight graphed on that z-axis, and we've got two of our independent variables down there on the base. Now we've got them colored by force, and if you're paying attention, you notice that the force difference between these three cases that ended up after we used Tecplot's filtering capability have a pretty large difference in force. In fact, if you do the math, you'll discover that the force difference between those three winning cases, if you will, the force between the largest winner and the smallest is almost 30%. And the weight difference between the largest and the smallest is only 5%. And so that's where your engineering judgment comes into play, and you say, am I willing to take a trade of weight of only 5% for a gain in force of 30%? And in most cases, you'd take that trade in a heartbeat. So these are things that having a graphical plotting package like Tecplot Chorus would really help you to see a lot easier. This is just another way of looking at these comparative images. The good thing about them is they allow you to sort of fixate on how these images differ, specifically in how they differ in weight, how they differ in terms of the force, and how they differ in that leakage. So you can examine them in a number of different ways. Here's a kind of an interesting comparison. That the starting configuration on the left, before we went right into integrated engineering's program, and we said, okay, move it into these 864 positions. Those are the dimensions that we started with. And when we finished with all those 864 positions, and we chose the winning configuration as that largest force of the three that you saw that we showed you on that previous screen, notice how drastically all those differences, all the dimensions changed. So it was quite a change. And of course, we see how much the force changed as well. So all of these, both a combination of integrated engineering and Tecplot, were able to bring us to in really short order. And even with all of this said, this was done with three independent variables. Now, there's a time when you're going to want to look at more than three, when you're going to have 4 or 5 or even 6 independent variables. And as the number of independent variables increase, so will the sparsity of your search space. It's inevitable. And when the data is insufficient, even when the data is sufficient, it can be overwhelming to try to look at that much data. So I guess what I'm going to try to tell you is that at one point you're going to have to use a combination of the mathematical approach with something like this graphical approach, especially as the number of independent variables gets large. And even when that happens, it's useful to be able to hold one or two of the independent variables constant and then look over the field space and take a quick view of how things are varying. For example, if X is being held constant, or Y is being held constant, or Z is being held constant. So Darrell is going to show you how Tecplot can do that a little more readily. So I'll give it over to him now.
Thank you, Ken. Okay, I'm going to quickly show you my screen. And let's just make sure. And you should see now at this point Tecplot Chorus, and it will take a second to refresh. So as Kent just pointed out, we're talking about highly dimensional space, and that's really what we designed Tecplot Chorus to do. And what we're looking at here are those sets of line curves where we're looking at the leakage, the magnetic leakage as a function of Z change, as well as the force as a function of Z. And you can see we're looking at a 3D space where I've actually applied an analytical model. In this case, I'm using a surrogate model. The surrogate model itself, in this case, I believe is just a simple quadratic response surface, but it's important to point out that, in fact, we're fitting 3-parameter space, not just 2-parameter space. And what that allows us to do is to evaluate changes in one of the dimensions interactively. So this set of curves is at a particular fixed X, and the X being one of the loops that we're trying to optimize. And one can actually now go through and analyze sets of X parameters and see not only how it changes the physical behavior of the system, but you can also see what that model might show you. And why surrogate models are really important in this context, we're talking about 3-dimensional space here. When you get into 5-dimensional optimizations, you can start to use emulators and other strategies to predict data points that you may not have. These extrapolated values, of course, are not perfect, but you can't look at all 5 parameters. I mean, 5 factorial worth of data would be thousands and thousands of results, and you perhaps may not have that kind of computational resources. So you can start to understand how one might be able to evaluate the dimensions of the data just by using this filtering mechanism. And so you can see there are cases where the behavior is it's not as well behaved as one would expect. And that's, again, where Chorus comes in, because you can say, well, there's something about this point here and this point here that just doesn't seem to follow the rest of the cases. And you can see that it identifies them down here. And what you'll see is that although the designs look almost the same, and we're looking at a matrix view now of the images, you can see that the forces are significantly different. We have one with a force of 9 pounds and the other with 52. So the question right away is, well, are they real? And this is where one can actually look at the images in detail. And we want to evaluate, okay, well, you can see that the designs aren't that dissimilar. I guess the biggest difference here being the Z, or the plunger shape, and it looks like in this case you have far more steel in this area than you do in this one. But the idea that you can then difference very quickly and see in effect what the difference is, and that can be done on 2 ways. Now with the data in this case, we don't actually have the physical data behind the image. In some cases you'll actually have the physical data, and you'd be able to click on this and open it up in a physics visualizer and actually do some additional interrogation. In the case where you don't have those data available, one can use the image differencing, which Ken kind of went over in detail. And it kind of, although from an untrained eye it may be difficult to see the differences, but in principle, if you understand the system, you can see what those differences are quite clearly. So when looking at the system in general now, by looking at what we call a matrix view, and again the intent here is to understand how those subtle changes in the system affect physical behavior. And we can walk through each of the different X iterations, and we're looking for anomalies. We're looking for areas where we have drastic changes in force. Like in this case, we have a force of 0.179, and if we look in this same matrix we have forces on the order of 27, 31, and it's the ability then to see not only what the physical system looks like, but to also understand quickly what it is that we're looking at in terms of the integrated quantities that come out of the system. And that's where we use Tecplot Chorus. Now this is as I said, it's only a three-dimensional case, but in principle one could actually be looking at multi-dimensional data, and we'll go back quickly and I'll show you this in 3D. So what I'm showing in this case, as you know, is actually being limited in X, but this is where you go back to that range filter. Now what you're looking at are all the cases, X, Y, and Z. And rotating this around real quick, you can see that our Surga model looks much different now, because in principle it's trying to fit all the data. It isn't actually limited, and it's fitting in X, Y, and Z. So it's a little less relevant in this particular case. So for those people who are doing optimization, who need to be able to try to find the physical drivers that might be influencing an optimal design, Tecplot Chorus allows you to evaluate the system performance and ultimately tie it back to the physical phenomena at a per simulation basis, which ultimately, in the end, helps you make a better decision because you understand what's driving the system, and it will keep you out of trouble. Because as Ken pointed out, it's easy, given the number of solutions you're looking at, to fall into a local minima and think that that's the optimal solution, or make a decision based on, well, look, this is the lightest configuration we can make, but as Ken pointed out, the ability to know that 5% increase in weight could yield a 30% increase in force helps you make a better decision. And that's really what we're trying to drive at with Tecplot Chorus. And with that, I'm going to turn it back over to Dennis, and we are going to summarize, and we have time for questions. So let me move that back over to you, Dennis.
Okay. All right. So basically we've gone over electromagnetics of solenoids and how you would use field solver software such as Magneto and Amperes from integrated to analyze and create model variations. And Kent has demonstrated a real-world example of how you would do this, and then using the Tecplot product, how you could make sense of all that data. So now we'll turn it over for any questions that you might have. If you haven't typed any questions into your panel, please feel free to do so now.
Yeah, so the way the questions work is you just have to, on the sidebar, you'll see an area where it says questions. And what you'll do is if you type in the questions, they'll show up to us, and we will go ahead and try to answer them. We have time for about 5 or so questions. And it looks like the first question is for you, Dennis. Do you want to go ahead and answer that?
The question is, can motors be simulated using rotational symmetric analysis? And no, because there's no such thing as a torque in rotational symmetric analysis. So normally motor designers are using 2D analysis for conventional radial flux motors. If you have an axial flux motor, then you have to do a full 3D analysis.
Okay, thank you, Ken. Let's see here. There's a couple other. Also, you can raise your hand if you have any questions. So,
let me just add one little clarification that Dennis is dead on with that. There are a lot of folks now investigating axial flux motors because of their usefulness with electric vehicles, being able to fit inside the wheel of an automobile. And there is a regime where you can try to cut one of those axial flux motors over a small region and sort of fold it out, if you will, and you can get pretty close for going after. You can sort of lay it out and it's simulated almost like a linear motor, and go after and use a 2D approximation, and sometimes you can get pretty close with that. But most people, 80 to 100% of the time, are trying to use the 3D approach. At one point, you have to abandon it and say, okay, now I need to get a little bit closer on my answer.
Right, and that seems to be typical across industries. You know, if you can use a lower fidelity or take advantage of symmetry, you go ahead and do so. The next question I believe, is about plotting the 3D data in Tecplot 360. In the context of the example we showed today, there is no direct input for the data into Tecplot today, but it's something we're working on, and between Dennis and I, we'll hopefully have a solution in the future that will allow you to open that data directly in Tecplot 360. Tecplot Chorus has a mechanism, however, which we call custom actions, which allows you to basically use any existing application to open up data. So in principle, when I showed you the selection of two results and wanting to go in and do additional analysis, in principle, one can actually launch that in any application. So it isn't limited to Tecplot per se, but our intent is to have a better data interface between the two codes. So good question. The next question, can you do a similar thing with CFX and Fluent? I suspect for those people who are not using CFD codes, those are both the ANSYS tools, ANSYS Fluent and ANSYS CFX. The short answer on that is yes. In fact, several of the example cases we have that we've tested Tecplot Chorus with came from analyses using Fluent in particular, to a lesser extent CFX, but I've been doing some work with CFX recently. Plan to have an example for that as well. So short answer is yes. And in fact, it works quite well. You can leave the data in its native format. You don't necessarily have to convert it to Tecplot. And it allows you to kind of look for those physical drivers in the system. So good question. Dennis, looks like the next question is for you.
Yeah, the question is about the permeability plots that I showed earlier. So that's the ratio of the B to the H field. No, we're plotting the differential permeability there. We could plot B over H, but we're actually using the slope of the BH curve. We find that gives a better indication of saturation. As I say, though, if you wanted to plot B divided by H, you can do that as well.
Thank you. We have time for just a few more questions. I'm going to look over and see if there are any people raising their hand. I'm not seeing that. So if you want to ask a question, just go ahead and type it into the box. Okay, so the next question is about Tecplot 360, and it's can you explain a little more about the models you use for surrogate models? Right now in Tecplot Chorus, which again these plotting capabilities are in the Tecplot Chorus environment, not in Tecplot 360. But the current models we're using for surrogate models are simple quadratic response surface and Kriging model. We do plan on opening it up so that if you have a particular emulator or a surrogate model that you are using and are familiar with, you'll be able to leverage that within the environment, within the Tecplot Chorus environment. We're also moving towards adding in capabilities for sensitivity analysis, and that will be something in the future. The next question looks like it's for you, Dennis. It's will autograph be discontinued? I'm not sure how to answer that one.
I'm not really sure. We are planning, of course, upgrading our plotting routines, but at this point, there's no plan to discontinue autograph until we have a replacement.
Okay, great. Thank you. We have time for maybe one more question. Dennis, looks like that question is for you.
Okay. I guess just a question about what types of steels were used in our models. For Kent's simulation, it was 1018 steel, and I used 1010 steel for my solenoid examples.
Okay. Thank you. Time for one last question. We'll give the audience an opportunity, or if you want to raise your hand, please feel free to do so. Okay, doesn't look like we have any additional questions. First, I wanted to thank you, Dennis and Kent, for a fascinating conversation. It was really interesting to see the application and how it fits into the work that we've been doing. So thank you both.
And thank you.
And also I'd like to thank the audience. So for those people who logged in, if you want to see the recording, it should be available and on the website by this afternoon, and we'll be sending out a quick note for that. Thank you again, everyone. Thank you, Kent. Thank you, Dennis. And thank you, everyone, for attending. This concludes our webinar for today. Thank you.
Thank you. Okay.